A software firewall on an operating system provides you no protection against somebody rooting that box and then turning off the software firewall, right? So a software firewall provides no actual protection against egress filtering on a protected machine. Software load balancers with TLS termination. It turns out F5s are 10 times faster than OpenSSL on a fast 1U box, but they're 20 times more expensive, right? So if you actually do the economics, it's almost always better to go buy your own off-the-shelf machines. And this is especially going to be true now that Intel Xeons have the AES acceleration built in. So as long as you're doing AES for TLS, you're almost getting as fast as an F5. The RSA sucks no matter what, right? But if you have to buy twice as many and that costs you a third as much, then it makes sense economically. So software load balancing with TLS termination on the software load balancers. The use of secure control protocols all the way through, not relying on network isolation to secure your control protocols, and per device PKI. So to go a little faster, one of the things we worked on with these people that wanted to do this securely is we built an overlay IPsec network, right? Because this is HIPAA data and they can't hit a lot of their requirements that they want to hit with the physical network because they don't control the physical network. We used a overlay network on top of the physical network to provide the same kind of isolation between all of their machines, as in we didn't have to trust Amazon's network. Not that we actually think there's a realistic attack where somebody walks into an Amazon data center and taps it, provides a level of getting rid of worrying about a lot of stuff that we otherwise would worry about. On OpenBSD, this is actually super easy to do this on OpenBSD because you can just create a certificate authority that issues certs for all of your different machines, and then OpenBSD will magically go and do IPsec. It's also very easy on Windows with domain joining and using Kerberos-enabled IPsec. It's actually a lot harder on Linux. One of the things that could be made a lot better. And then we use cloud glue services. Instead of something like a direct database connection or a direct web service connection between the web service and app tier that's one-on-one, we use asynchronous web services, message bus, and queuing services. So this is from Amazon's best practices thing, white paper. And this is what the recommendation is, that instead of having my web tier, app tier, database tier, or whatever I want to call them, directly coupled, synchronously, tightly coupled, and having a human being have to log into these machines to create these relationships, I use scalable queue services where I pop data on and off a queue, and I do so asynchronously without knowing who's at the next level, right? So Amazon provides this, a simple queue service, where you make a web service call where you can pop data onto a queue, and then that data can be popped off by somebody else that has the same credential. Now, do we trust that data? Maybe we don't. We don't trust that queue service. It belongs to Amazon. We don't know how it's implemented. But we don't have to trust it, right? We're only trusting Amazon to provide us with lossless connectivity here and to provide us with the scalability to make this work. So what we do is we use symmetric encryption keys on these guys so that for every type of message, there's a symmetric encryption key that encrypts that message when we pop it on and off the queue, right? Which is just as fast as if we did MySQL or Oracle over a TLS-connected TLS connection. In fact, might be a little faster because there's no asymmetric cryptography. We talk about using a database replacement. Single instance MySQL, like I said, is really bound to disappoint you. There's been a lot of good work on NoSQL databases, CouchDB. There's things like SimpleDB, which is Amazon's product. Bigtable is Google's internal product that if you run on their app tier. Microsoft's got some kind of magical distributed thing that looks like SQL Server, but obviously isn't because it runs on 10,000 machines. That kind of stuff. CouchDB is pretty popular with people. Mondo, anybody heard of Mondo? That's a pretty popular one now too. Most of these are document stored. They're not really SQL, so you can't do normal SQL in front of them. Although some people are building layers to take SQL commands and then to turn them into the web service calls that these databases understand. So like I said, you don't have to trust these. You can use access control. You can use cryptography to enforce your access control. And this is where the security protections we put into the system to protect against our cloud issues also help us make our application more secure. So folks that we're talking about, we're using per entity encryption, identity-based encryption on per login, and every institution that logs in, not every individual, but every time somebody logs in from an institution, they have their own set of keys used to decrypt certain types of data, and that data, especially the PII as defined by HIPAA, is stored encrypted in the database. And the application tier has to go ask a service and say, Dr. Jones is logged in. This is Dr. Jones's usernames and passwords. Please give me his decryption keys, right? And we have our trusted service hosted elsewhere that has certain logic on it. And that logic does things like, okay, well, Dr. Jones, this app server's only asked for 10 logins in the last couple of minutes, so that's fine. You haven't asked for 1,000 logins. And yes, this is the correct password, so here's Dr. Jones's key. And now the app server in its web session layer automatically decrypts that data when it comes in and before the Ruby level sees it. So there's a Java level below Ruby. Yes, sir, you have a question? We kind of rolled our own on this one, yeah. This is definitely the kind of thing where there really needs to be a good common product. There's lots of opportunity here for somebody to build this and make it standard, yeah. The IPsec stuff, obviously we used off-the-shelf IPsec stuff, but for this encryption we had to roll our own. That's a good question. One of the reasons we rolled our own is because we only have to encrypt certain fields, right? And those fields are pretty much static. So the social security number and the health records of individual people, but not their names, for example. So because of that, we implemented the encryption in the class definition itself. So the class itself, the object, the patient object that you pull out of the database actually does the encryption and decryption itself. And then that object gets serialized into the database. How do we get these secrets onto cloud VMs? One option that we've been looking at that we have this working, it's not really in deployment right now, is one of the things you can do to make this kind of stuff really easy is you can do CH roots, and you can build secure CH roots and encrypted like tar files, store them on S3, and then push out your AMIs, have your AMIs boot, and provide those AMIs within their boot script. So on Amazon, you can provide a boot script that runs after an AMI boots up, an instance boots up, and in that boot script, we pull down, decrypt with a symmetric key that's with a PGP key that's built on there, decrypt the tarball, and then enter into the CH root. And this makes patching a lot easier because all of the running services are within the CH root. There's no running network services outside of it. So if we need to patch something, all we have to do is patch the CH root itself and not patch the AMI instance. And then we tell the AMIs to go get new CH roots, which we have a script to tell them to go do that. And so that's one thing you should think about when you're on the cloud, is think about using normal like Linux encapsulation technologies to encapsulate something smaller than the operating system that actually has the software and the configuration settings that you want. So what we end up with in a system like this is that we still have security groups because these security groups have to be used to provide access from the outside. So like the web proxy group, you can get in on 80 and 443, and these guys you can't. But for all of their connections to each other, we're doing that all IPsec over an overlay VPN network. And in fact, based upon our configuration, these guys can basically not talk to anybody except over IPsec using a local config in there, which is stored in the CH root. We're using Amazon Simple Queue Service and Amazon Simple DB, which, like I said, on an individual basis is no faster than MySQL, but from a throughput perspective is much, much faster. So you'll get way more throughput out of Simple DB from 50 or 100 app servers than you'll get from a single MySQL instance, even though there's a little higher latency on every individual request. And that data is stored encrypted with those keys distributed from a key server, which we're actually putting in a data center our client owns. And the way, when somebody logs in, those credentials pass through the app server tier, and then the app servers go to the key server and say, can this guy log in? And he says, yes, he can. This is all over IPsec. Here's your encryption keys, and then those encryption keys can be used to put messages on and off the Simple Queue service and to pull data out of the Simple DB. And then all these configs are stored in an S3 bucket encrypted, and if we want to update or patch an app server, we take one of these CH roots, we open it up on a workstation, we run apt-get, and then we package it back up into a tar gzip, and then we just kick these machines to make sure they go get those. And we can kick them without really worrying about, we do actually have the software has a function to go flush sessions, but we don't have to manually go in and say this app server is going down because the app servers are just pulling things off of the queuing service, which adds a little bit of latency, but in the end, the latency internal to this is nothing compared to over the internet latency, and people don't notice a difference. So the things that still need to be done, making this PKI easy for this and PKI easy for this, something that should be done, right? In Windows, it's pretty easy. In Linux, it's very difficult to do, and there's no real commercial products that I've seen so far. The configuration management can be made easier. RightScale actually makes a lot of this easier. Making this as a standard middleware tier would also be one way you could do it so that people don't have to run their instances, that all of this stuff is actually part of a middleware tier, which is interesting because I think Azure Microsoft's platform here is going to be a big player, and kind of if people want to do this as a platform as a service. There's still some better ways to cloud in the box products that we have to wait for. And a real big problem is that the standards regimes can't really understand this. Fortunately, HIPAA, despite everybody talks about HIPAA being horrible, but one of the reasons HIPAA is horrible, it has no standards, right? Like they don't actually tell you what to do. Unlike PCI that has much more specific requirements. And so we can make this work because we're able to convince the lawyers that the protections we put in place are equivalent to the protections you have. There's no way you could do this, even though I feel this is more secure than a standard a stack in a data center, you cannot get PCI certification. Because PCI is much more specific in things you have to check, and a QSA is not going to have the flexibility to say, oh yeah, I see why that's better, right? They have to say, I have to inspect your data center and walk down the row. No, it's better because I have to walk down the row in the data center. Okay, great. I'll use PayPal, right? So something that definitely has to adjust so that people can do this kind of stuff.